Boom. Ladies and gentlemen, welcome to Honors Math 1. I'm your teacher. I'm back. If I was here today, we'd be doing section 711, talking about isosceles triangles, equilateral triangles also. This is obviously something from German engineering design on here. I usually start with something like this, a little picture of this. You may have seen a bridge like that. It asks you what type of bridge that is. It's called a cable stay bridge. And each of these cables are supporting the weight of the bridge using triangles. And as you can see, each of those are isosceles triangles. It's a series of isosceles triangles where this cable is the same length as that cable. And this cable way out here is the same length as that cable way out there. One of the ways they verify and make sure this bridge is still holding its weight properly is if this side is the same length as that side, there's a lot of symmetry going on there. And they can check that things are symmetrical as this thing supports the bridge's weight on there. This is typically, maybe this will come up in a second here. This is typically something I'd have for a warm-up for you to do. This is not, I haven't provided this for you. So take 2 minutes and try this on your own. You just have a scratch paper, just see what I'm looking at here. Hopefully you can see all three of those questions. Ask you to reflect this triangle into side BC, like that's like the line of symmetry. We're talking about parabolas. That's like a line of symmetry. So reflect that. And then draw some conclusions about the new triangle, A prime, B prime, C prime, as well as some conclusions about this triangle, A, C, C prime. This is an important one we're going to talk about today. And then we'll come back in a moment to talk about isosceles triangles and the date that would probably be, roughly, hopefully you're doing this around March 24th-ish. Let's see if this lets me right up here.
Are you done with that sentence?
No, we keep going. So, if you did this, you would have flipped this triangle over here. Perfect. A is now A prime over here. B and B prime are technically the same thing. They didn't move. And C and C prime are the same thing. So those didn't really move. They're the exact same locations because they're on a line of symmetry. If I was in class, I'd probably ask you, how long is A prime C prime? And you'd very quickly go, hey, it's 13. It didn't change. It's still the same length on there. And then I ask you to make a conclusion about this new triangle, A prime, B prime, C prime. One of the conclusions you could come up with is that it's a right triangle. You might also say it's scalene. That's also true. Scalene. The big conclusion, and of course if you spell that wrong, somebody will criticize you. You know what I'm talking about. I know I wrote an S there a minute ago. The other conclusion you might come up with is it's congruent to the original triangle, or A is congruent to A prime, or more specifically, angle A is congruent to angle A prime. Because of this idea of its being a reflection, it didn't change size, it just flipped over. This angle measure has to be the same as that angle measure. There we go. Another conclusion, I don't know why I didn't like two of those. Another conclusion I want you to think about is the big triangle now is isosceles. I don't know why I didn't like these. It's an isosceles triangle. Why? Because this 13 was reflected as the same. So it gives you some features of this. If this is really an isosceles triangle, this angle got reflected over and is therefore congruent. That is something called the base angles theorem or the isosceles triangle theorem. I used to call this the base angles theorem. If I give you a textbook, they'd call it the base angles theorem. That's what these first two theorems are on your paper. There's a lot of practice problems in this homework and in this set of notes. Not a whole lot of new stuff we're throwing at you. Just making you aware of a theorem. It's a theorem, so we have to prove it. We're going to prove it in a few more days because we're not quite ready to prove this thing yet. But just to add some knowledge, some vocab to your mind here. The sides that are the congruent sides, so I have little congruent marks on yours. Those are called legs. You might know what the other one's called. It doesn't have to be the bottom, but it is called a base. It's called the base of an isosceles triangle. These two angles here are sometimes called base angles. The other angle, and you got to know this just in terms of reading word problems and things like that, you're going to come up. The angle that's across from that base is called the vertex angle. That just happens to be the vocab term for the sort of the unusual angle, the oddball angle. These two angles are the base angles. They're symmetrically the same. Example of symmetric property. You're probably filling all the words on here based on the marks I just showed you. The first thing I put up there was sort of declaring that it's isosceles. And this is called the theorem. There's a converse to this down below. If it's isosceles, you know the two sides of, it's got two congruent sides. So the given in this case would be if there are two sides that are congruent, you're going to know other things about the triangle. And I've sort of mentioned these on 7-9, I think, one of the last sections. The something opposite of them are also congruent. And of course, the things that are opposite of them would be the angles that are opposite of them are also congruent. That's called the base angles theorem. There's another version of this. So if you know these two are congruent, you also can prove those two are congruent. Take a minute. There's a converse to this, which just means the logic is flipped around. The given is the opposite of what you're trying to prove in the sentence, in other words. See if you can fill in those blanks there, knowing this should be the opposite logically of this first statement. I'll be back again in part 2 in just a moment.